All right, so let's go over to the code for this. See how big I can make it. Hope you guys can see this. Okay, so this is nothing new here. You've got your libraries that you're included, and what we're going to do is make this is the entire system. This is including the music player. This is the signal out of the music player. This is that square wave at 250 hertz, that middle C. This is the button that comes in, tells the doorbell circuitry to send a start signal, and a clock signal. Okay, first circuit that I'm going to describe here is, it says doorbell. Okay, so the architecture is doorbell. Inside a single architecture here, I have two processes. One that describes the machine that sends the start signal, and the other process is the music player. Okay, but for this entire architecture, let's see, takes these signals, and okay, and all right. Then we're starting right out with state type. Remember, we just did this in the slides here. Blazing fast computer. Where we used the type keyword there, and then named our own type of data, and then we gave a list of the values that a signal of this type can have. So again, NS and CS can only have the values S1, S2, S3, S4, S5, S6, or S7. So right here we have type, and then again I named it state type, but I could have named it, you know, Alfred. It doesn't matter. That's up to you. And then is, and then here's the list of the state names that I'm going to use. And you can tell that this is for the doorbell part of the circuitry. No button, and the signal and the music is done. So that's kind of your wait state. And then you have the button's been pushed and your start signal's going out, and then you have the button is pushed and you haven't got a done signal, and then back to then the button's still pushed, but you're done. You've gotten a done signal. We'll come back and talk about that a little bit more in a moment. Okay, and then just a few signals that we need to work with. And right here, we've declared a signal called doorbell state, and the type of that signal is called state type, which means it must have one of these values. And it does. It has that first state, that wait state. It's initialized to that first state right here. Okay, and here's a description of the music player. I did the music player first. Okay, when the start button is pushed, a 250 hertz signal is output for 1 second. 250 hertz signal is a square wave, a 0, then a 1, then a 0, then a 1, then a 0, then a 1. Okay, and the logic behind that is that, again, we've got the 50 megahertz clock, which is 200,000 times faster than 250 hertz. So the clock must be divided, and I think you've seen that in lab by now, what a clock divider looks like. And what that means is, again, that every 100,000 clock cycles of this fast clock, the 50 megahertz clock, the output needs to go from high to low or low to high. Okay, so I did, let's move this out of the way. I did a couple of styles here for the music player. For the music player, I just used if-then statements. Okay, for the doorbell circuitry, I used proper state transition diagram kind of notation. So let's look at what the music player is doing here. This is kind of hard to see. Let's see if I try. So here's the music player. Declared a few variables here. Okay, so if the music player is a process and its sensitivity list includes the clock only. So when the clock ticks, every time the clock ticks, it goes through and runs this code right here. So if the clock ticks and start equals 1, then I initialize the values for the music player to start to play. Okay, the V out cycles is your 250. So you need 250 cycles of a 250 hertz clock to 250 of those cycles will take exactly 1 second. And then the clock cycles, that is the one where you have to count 100,000 times to divide down that fast 50 megahertz clock. Okay, so if we've got a rising edge on the clock and you haven't seen 250 cycles yet, then you count up your clock cycles 1 time. If you haven't reached the 100,000 clock cycles yet, you count it up 1. If you have reached 100,000, so every time the clock ticks, you count up the clock ticks until you get to 100,000. And if you have reached 100,000, then that output signal, if it was 0, then you make it 1. If it was 1, then you make it 0. In other words, you just switch its value. Remember, every 100,000, you need to, if it's high, it needs to go low, and after another 100,000, it goes high. And in that way, you end up with a square wave. Okay, and then you need to start counting the clock cycles all over again. You need to start counting the next 100,000 clock cycles. So this is sending clock cycles back to 0, so it can start counting that's 100,000 again. And if you do reach 250 of your 250 hertz clock, then you need to tell the other sequential circuit, your doorbell, that you're done. And just for safety reasons here, I set the output to 0. So the thing that was a square wave, that 250 hertz square wave, now it's just going to be set to 0 and stay there. Okay, and then you only want the done signal high for 1 clock cycle. And remember, here's something handy. Let's see, this might actually go for 2 clock cycles. Bummer. Okay, I have to check this, but done is set to 1 here. Because this is a signal, this will come through and maybe on the next clock through sees if it's a 1, it'll reset to 0. But I think actually done might be high for 2 clock cycles. This is one of those places where you can get into trouble mixing signals and variables. So yeah, I think maybe want to